the motion of an orbiting star and finding the launch speed of a ship from an orbiting planet that will enable it to approach the black hole without crashing and being able to leave the system. The physical principles relevant to this lab are Newton's laws of motion, including Newton's second law and the position and velocity update formulas, the universal law of gravitation, the average speed for non-constant forces, and the parallel and perpendicular forces. By calculating the change in momentum of the star on each iteration, the net perpendicular force acting on the star was found. Through the universal law of gravitation, the mass of the black hole was estimated to be roughly 1.38 times 10 to the 34 kilograms. By trial and error for a fixed vertical launch speed, the horizontal launch speed was modified. For a discrete time interval delta t, knowing the initial and final momentum of the system, the net force can be calculated as a change in momentum over the time. Once we have calculated the net force on the star, assuming the gravity is the only force acting on it, we can find the mass of the black hole. The black hole is considered stationary, as it is much more massive than the star. For part 2, we considered all the forces acting on each object. Because the black hole is much more massive than the other bodies, it is considered stationary again. It is also unlikely that the spaceship will have a big effect on the planet's motion due to the same reason. For the first time step, we calculate the net force on the ship, and then we update its velocity and its position. The same process is done for the planet. The forces are recalculated with the new positions. The motion for the spaceship and the planet is tracked. By altering the initial speed of the ship with the code, we will be able to find a reasonable speed for a close approach which will be less than the speed of light. In part 1, the system is the orbiting star and the surroundings is the black hole, while in part 2, the system is the spaceship and the surroundings are the black hole and the planet. Here, the initial conditions for both part 1 and part 2, including the mass of the bodies, the gravitational constant, and the time interval between data points, are included. In part 1, the star's initial position is in the aphelion, and in both parts, the black hole will always be in the origin and stationary. In part 1, based on the seed, the computer model takes the star's initial and final velocity for the first time interval and computes its change in velocity and momentum. To get the net force acting on the star in this interval, it divides the change in momentum by the delta t. Then, it finds the parallel and perpendicular components of the net force, and it calculates the mass of the black hole considering that the net force is equal to the force of gravity. In part 2, the model calculates the force of gravity on the planet due to the black hole. Then it calculates the force of gravity on the planet by the spaceship and computes the net force on the planet. It follows the same process to compute the net force on the spaceship. Using the position and velocity update formulas, the model updates those values for the planet and the spaceship. The program recalculates the net force and repeats the loop for each time step. Here's the simulation for part 1. Taking the force that acted on the star in the last day, the mass of the black hole was estimated to be 1.3825 times 10 to the 34. However, to improve the accuracy of the results, the mass of the black hole is calculated taking the average of the masses calculated for each day. After trial and error, this is a successful simulation for part 2. Some possible sources of error are that the time steps are discrete, hence there could be some error committed in the position, velocity, momentum, and mass calculations in both parts of the lab. Also, there can be rounding errors due to the precision of Python data values and because of rounding the mass of the black hole in part 2. The ideal speed in lab 2 is found by trial and error, not by mathematical means. The net force and the rate of change of momentum are equivalent. While you need to know the value of the mass for finding both, for computing the rate of change of momentum, you only need to know the change in position and time, whereas for the net force, you need to compute the acceleration of the object, which is harder to do. For the spaceship to enter into an orbit around the black hole, the x-component of velocity should be much slower so that the body does not escape the system, and the y-component should be larger so that it does not crash into the black hole. The trial and error, a possible initial velocity was found to be. In conclusion, the mass of a black hole can be calculated with reasonable accuracy with a computational model by simulating a two-body problem with one object being the stationary black hole and the other being an orbiting body. It is significantly easier than carrying out the calculation in real life, as we would need to wait more than 400 days for a full rotation, and the measurements would be very difficult to take. Also, the land speed required for a spaceship to leave the system of massive bodies can be found by trial and error, knowing the mass of the bodies in their initial position. An optimization for finding the lowest speed can be carried out by repetition, but I do not know if it is possible to do this calculation analytically or with a computer to find the exact value.